All right, welcome to Amber Book 40 Minutes of Competence. We have a fairly short one today. So imagine, if you will, you're working with an old-fashioned Dixon Ticonderoga pencil, and you're getting frustrated, and as your frustration grows, you have an urge to break that pencil. And imagine, if you will, you have three ways to break the pencil. You can, if this is the pencil right here, you can squeeze it to death until it eventually breaks, being careful not to bow it one way or the other. You can pull it apart until it breaks, so you can rip it apart by yanking on one end and yanking on the other, or you can bend the pencil where you're hoping it'll just kind of split open from here and then break open. And you know, of course, bending the pencil is the most efficient way to break the pencil, if efficiency is measured in breaking pencils and not keeping them. But your axial forces, the one that run along the axis, the kind of along the axis of the pencil is obviously much stronger if it's on the if you're trying to pull it apart by either pulling it directly apart on its axis in an axial way, or squishing it together in its axis on an axial way and avoiding any kind of moment, bending moment. So that's generally what we need to know for this, because when we're thinking of buildings, at least in school, I think it's pretty natural. People think about the gravity loads and they just kind of think about them going down to the ground. Actually, I think people are good with gravity loads going to the ground. They kind of forget that they have to rest on the ground. They're certainly not very good with any kind of transfer loads if you kind of have to move over for a column here, so it comes down and over and down. But one of the other things that we're, I think, intuitively not, until we get a little bit farther along in our career, intuitively not thinking about a lot, is that there is a significant amount of work and kind of non-intuitive work that goes into resisting lateral loads. And what causes lateral loads? Well, we're talking about wind and we're talking about seismic. And so what we want to do is we want to use something to prevent some kind of a skeleton building in steel in this case. And this is where steel this is most, steel kind of mid-rise and high-rise buildings is where this is most applicable. And we want to have something to avoid where this whole building kind of moves over. And each bay, if I can kind of zoom in one bay here, each bay, like that, in the event of major lateral force, it wants to become a parallelogram. It wants to become a parallelogram. So how do we deal with that? Well, there are several different ways to deal with it, and almost all of them involve taking one or two bays of facade in the XZ and a facade in the YZ dimensions and making them somehow resistant to lateral loads. We don't typically have to do it with all 9 bays in this case. Usually 3 are fine, assuming that this is ground floor and that these are kind of underneath in the basement. So one way we can do it is we can make this wall such that it's constructed of concrete or reinforced concrete block, or some kind of panel material like a rigid enough wood or a rigid enough steel. And we can make it so that by filling in that bay with that material, it is resisting when there's kind of this force that wants to make it wants to make that bay look like this. That panel acts as a way to resist it, and that's called a shear wall. Now, oftentimes we don't want to use a shear wall because maybe there's not enough support for it down below in terms of the soil being competent enough to hold the extra weight. Or more likely, maybe we want to punch a bunch of holes in that facade for windows and doors, and especially on the first floor, and we may want to just make it so that so that we have something a little bit lighter. And so one way we can do that is we can make beefier connections. So we can make what are called moment connections, which kind of in practice make it like this. Kind of diagrammatically. And we're essentially making each of these connections such that it is able to resist the lateral forces that are coming into it. And of course, from a design point of view, if cost is not an issue, that's probably the easiest thing to do. You just declare them all moment connections, all the joints moment connections, and look at that, now you've dealt with all the problems. And you've kept all of your bays clear so you can put a window or a large storefront in all of your bays. And it's important that whatever decision you make, it extends not just like 2 of the bays down, but all the way to the ground. That's kind of important. And it's important that the bay itself is wide enough. You know, if a bay was really, if we had theoretically a bay that was this narrow, then of course, going like that, it really kind of behaves more like a column. It doesn't do a good job of resisting because it doesn't have enough area, you know, kind of over that panel, over that facade. So anyhow, this is make everything, so this is called a shear wall. And then making all the connections, moment connections, is another option. And the problem with making everything moment connections is that they're pretty expensive. They're pretty expensive. They're surprisingly expensive. You'd think it would cost more, but until you have to put a few more bolts in. But because these are very skilled, highly paid people working high in the air, doing all these moment connections, it turns out, is often very expensive. So that leaves us with these other options, which is bracing. And the idea behind bracing is that if you have this this rectangle that after the introduction of an earthquake or a heavy wind load, hurricane, wants to do this, if you have your bracing like this, well, now it's trying to rip apart the pencil by pulling it. And that's hard to do. So having that bracing here will limit the likelihood that your panel will become this kind of parallelogram. And likely, having the bracing this direction will mean that you are squishing down the pencil. And just like breaking the pencil by squishing it down together is a very difficult task, it's very difficult for this building to get into a parallelogram. It's going to want to stay true and plumb and rectilinear and orthogonal. Now, in terms of types of bracing, which is really the meat of what I want to talk about today, we'll start with that one. We'll start with this idea that we can just have a diagonal. And again, we're assuming this is a ground level. And there's a diagonal, and that works pretty well. In fact, that works about 2.5 times better than not having the diagonal bracing. So a single diagonal works pretty well. It will stiffen the structure in resistance to lateral forces. The other one you're likely familiar with is cross bracing. And in cross bracing, we likewise are keeping our building resistant to lateral forces, because should the building deform, then one of these goes into tension and one of them goes into compression. In fact, of all the ones I'm going to show you, the cross bracing is the only one where it's kosher that both of them can be cables. Both of them can be thin rods. Both of them can be wires. So with cross bracing, because it goes both ways, whether it wants to deform like this, then that will pull this one farther apart, and so it's in tension, so a wire or a rod can handle it. And if the wind's blowing from the other direction, and it does this, it wants to do this, then this wire would hold it together and resist that. So we can, in the case of cross bracing, both of them can be in tension, both members. Now, there are other types as well. We have what's called V bracing, and it's obvious why it's called V bracing. And we have what's called inverted V bracing, or chevron bracing, because it looks like the kind of the icon of a chevron, and that looks like this. And then we have K bracing. There are two different flavors of K bracing. Sometimes it comes all the way, you can see why it's called a K. You know, if you kind of include this, looks like a letter K. But we have K bracing, where we're going from the corner to the column and then back to the corner. And then we have a different kind of K bracing that does this, where it's like a little, the K in each case is going halfway across, halfway across, halfway across, halfway across. And in each of these cases, the job of these guys is to resist lateral loads from seismic or from wind. Now, how do you know which one to use, and how do you know which one to use when? Well, there's all these factors that are going to come into play. There's weight and stiffness and resistance and ductility and bending in the floor beams and the likelihood of column failure and seismic and redundancy and strength and energy absorption and deformability. So it's really the purview, both in terms of your career and in terms of this exam. It's beyond the pay grade of the architect. This is more of a structural engineer decision. But there are a few things that separate these, and I don't think it's that important that you know these. Like for instance, this cross bracing or X bracing, when you tighten it up, it can cause the floor to be in bending. So it can kind of squeeze the floor together. So that's a bit of a downside, bit of a bummer. And this K bracing, in the event of an earthquake, sometimes the K bracing here, because there's so much force at this midpoint of the column, and same thing with here, at the midpoint of the column, it will buckle the column and cause failure. So generally we try to avoid K bracing in seismic, but generally the most important thing is actually a pretty architectural reason, and that is we want to compose the facade. So it's facade composition that's actually going to drive this. So if we wanted to have a window in the middle of each bay, you can see how a single diagonal can become problematic. Likewise, cross bracing, if we want to have an aperture in each bay, a window or a door, you can see how cross bracing can kind of block it. Now there's lots of good examples of architects who have used that kind of bracing and as a feature, not as a bug. But that's why we often don't use, or sometimes don't use that, cross bracing or single diagonal. And sometimes with a V bracing we can get away with a window, but maybe we can't get away with a door. It becomes a bit more difficult if there's a door here and there's a V in the way. And with the chevron, we can do windows, depending, you know, if they're small enough, and we can actually have a door, and that works out pretty well. With this kind of half K bracing here, that opens up the middle, so we can have windows, so that's not a bad idea. So, of course, again, it's generally not recommended for seismic. And they have different strengths. Like I mentioned, that this one is actually 2.4 times as strong. This one is 4 times as strong as not having any bracing. So they have different strengths. But generally, from the point of view of the architect, you're really concerned with apertures and facades generally, and composition of facades, and how's this going to work. So, and then you should also probably know that in seismic performance, generally our goal is twofold. One is to have minimal weight So you want a lightweight structure. And the other is to have a ductile structure. And ductile is pretty much what it sounds like. It means you could kind of bite your teeth into the structure and it would deform without breaking. So it can stand large deformations without failing. So in a major earthquake, it'll bend but not break. And so each one has its own kind of deformation that will happen in an earthquake. In the case of the chevron, this is the fear, that it'll do something like this, and this one will buckle, and this one will stretch. And so for an earthquake, we generally want something else. We want to eccentrically brace the building. So these are all different eccentric bracing, and then this is kind of how they well, bend but don't break in an earthquake. I was going to say fail, but it's actually kind of success. But the most common one is to use the chevron. And what we're going to do in each case is, you see, instead of meeting in the middle, we're meeting just offset. We're meeting offset. We're meeting offset. This is the eccentricity of each of these. And so if it was a chevron and this was in a seismic prone area, we would do something like this. And then of course down here we may have, some kind of a panel because it's a concrete basement. And of course you can see this also has the advantage that it opens up the middle quite nicely for apertures or windows or doors. Now, if you are looking at a facade, let's assume this facade is a garage for repairs on tractor trailers. So tractor trailers pull in here. And this is the double door for humans to enter, and this is the right here is the opening for the garage for tractor trailers to enter, and this kind of bay over here, this bay here is maybe the storeroom for the parts. So if we were trying to get this building to resist lateral forces from an earthquake or from wind, we would put the shear wall, or we would put the bracing in that bay. So assuming there's a bay there, and a bay there, and a bay here, and that we need to stiffen it in one bay to resist lateral forces. We can resist it like that, and we're done. Or we could put cross bracing, or we could do a shear wall, or just about anything we wanted we could probably do. And it would be hidden or visible, but it wouldn't interfere with the aperture, because of course we wouldn't want to put it here. The tractor trailers can go through, and here we could probably squeeze it in, but it gets to be a little bit difficult. Now, if we have two bays, let's say we have our storage not on this facade, but our storage is on the back of the other side of the building, what we're looking at. So we have two bays where two tractor trailers can pull in, and the storage is in the back. Well, now we're a little bit more difficult, because we have a bay here, and a bay here, and a bay here, and we don't want to do that, and we don't want to do that, and we don't want to do that, because in each of the cases, the door, the garage door, or the human door, gets blocked by the cross bracing. So maybe we're talking about something where, if we think about the three bays, and of course one option is always, it's kind of the nuclear option. It's just to say, well, it's all welded in a way that it's moment connections, so it's not a big deal, or bolted in a way it's moment connections. So we've just dealt with it, and we can kind of, we can kind of just brush our hands off and be pretty proud of ourselves, and just kind of be done by saying, okay, we're going to make stiff enough connections up here so that it's not an issue. But if we don't want to do that, there may be another option, right? So something like this, maybe if that column is here, maybe we can do something like a chevron, where we're out of the way of the door, and we've braced the building appropriately. So that may be an option. We certainly wouldn't want to do We probably wouldn't want to do a K. We probably would not want to do cross bracing. And it's probably wide enough that we're okay. Generally, the rule of thumb, and it depends what you're what you're building of, but we can get typically a ratio of 3.5 to 1. Any more slender than that, and this starts to behave like a column and is not really able to resist lateral forces. All right, well, let's go to last week's question. You might remember that somebody had the really good question last time and said, what is RMC, IMC, and EMT conduit? I added GRC as well, and I said, I will get back to you. And now here I am, I'm getting back to you. So these are all classifications of conduit, and we're classifying them by wall thickness, generally. So RMC is the thickest. It stands for rigid metallic conduit. It's the conduit we often see for bigger wires or wires that are spanning longer distances. It's thicker and it's threaded so that you can screw one conduit into the next one, maybe with a coupler or something, and then you can sleep well at night knowing that the conduit, if one of them gets bumped into or ripped out accidentally, it's not going to cause a big problem all the way down the line, and it's going to be able to resist getting yanked a bit because it's attached to all the other conduit, which is attached to all the structure. The next thinnest is called IMC, or intermediate metal conduit. So RMC, or rigid metallic conduit, that's our baseline. It's thick and it's threaded. Intermediate metal conduit has a medium thickness. It's also threaded, and so it's for smaller circuits or shorter distances in spanning. And then our thinnest is called electric metallic tube conduit. So EMT for electric metallic tube. That's the thinnest. It's actually sometimes called thin wall, and it's too thin to be threaded. So in the case of electric metallic tube conduit, it's not going to be threaded so that one can screw into the other. Now there are kind of couplers that can link them together somewhat, but generally this is more of a lightweight kind of deal. It's for smaller circuits, which we call branch circuits, kind of the last circuits leading from the, say, the electrical room on your floor to your receptacle at your outlet, at your desk. And it's not designed for robust connections to the conduit upstream and downstream. It's less expensive, that's why we use it. Now, GRC conduit, which I don't think was asked about, but it's probably worth covering if you're covering the other three, is galvanized rigid conduit. It's just galvanized, so it's galvanized for corrosion resistance. So if you were running that conduit like outdoors in a marine environment where there's salt air and maybe some salt spray, you certainly would not want to use conduit that's likely to rust quickly. So that's GRC, or galvanized rigid conduit. All right, now for next class, for next time we meet, here's your question. Someone had asked before, they said, you need to cover some practice management. So, okay, this is some practice management we're going to cover. What specifically does a firm need to do to assure quality control, often called quality management or quality assurance? So what specifically does an architecture firm do to achieve quality management, quality control, and quality assurance? That concludes our 40 minutes of competence today. And I'm gonna go ahead and give you guys a minute to leave if you want to leave. But I'm also going to unmute you so you can ask questions.
Can I ask you?
Sure.
Okay, fine. The first one is pillar. So we're using shear wall in steel construction.
You asked if you can use shear wall in steel construction?
Yeah, like.
Abso-freaking-lutely. It's done all the time. And what's often done is if there's going to be steel construction, now I'm looking at it in plan.
I mean, the shear wall for steel construction.
Yeah. No, shear wall. It's done all the time. So if we're looking at a building in plan, like the dorm that's being constructed out my window. Let's say we have a grid of columns that looks like this in plan. Often what will happen is for fire resistance reasons, you'll need stairwells, and those stairwells have to be non-combustible, because the idea is if the dorm catches on fire, we want to make sure that people can get out of the dorms without having the fire spread to the stairwell. So what we'll do is sometimes we'll make either either site cast concrete box here in plan, and another one here typically. So at the end of the hallway, on either end, the hallway will be here, and the dorm rooms will be all in here. And so we have to often make that out of something non-combustible anyway. So we'll make it either out of site cast concrete or concrete block that's grout filled and reinforced. But in those cases, then what we're going to do is because it has to be concrete anyway, or concrete block, and we'll just go ahead and reinforce it. We'll use those as the shear walls. So depending on the seismic loads and the wind loads and the size of the building and the weight of the building and all the other things that go into effect to determine how much lateral resistance you need, it's often that the stairwells on either end are actually, if they're panels that are resistant, that's enough, and we no longer have to brace anything, and we don't have to do any other shear walls. So that's kind of a common hack, design hack, cost hack, whatever.
As you were saying at the beginning that we don't want to do because of the soil, another condition we want to avoid that, and we want to use bracing instead. So is bracing cheaper than shear wall, or shear wall is the cheapest?
No, it depends, but often bracing is cheaper than shear wall unless, and this is a big asterisk, unless you have something like a stair tower that has to be built of concrete anyway. In which case shear wall is cheaper than bracing because you're already building the shear wall because you need it for fire reasons. Or unless you want to have a concrete wall there anyway. Or unless in wood construction, often the OSB that forms the enclosure on the outside of the building is the shear wall. So shear wall is the cheapest if you need it anyway for enclosure or fire resistance or something like that. But if you don't need it anyway, often bracing is less expensive.
See. And my the last question is that when we talk about bracing and moment resisting and even shear wall, I know that especially from moment resisting frame, we consider all columns and columns, right? Not only just the exterior.
Yes, correct.
So that applies for bracing.
Oh no, I'm sorry. Yeah, when you said we consider, I thought you meant we take them into account. No, the bracing would usually only be, so basically you need something let's go back a few. You need something let's say this is the building here. All right, you need something in all three planes. So you need something somewhere in this plane. So we'll call that we'll make this X, we'll make this Y, and we'll make this Z. You need something in the XZ plane to resist lateral forces, whether it be bracing or shear wall. And it doesn't have to be all the way across. And it doesn't have to be in the facade. We could have it in a plane that goes like this. So we could totally have the resistance on the inside. it's more efficient and effective to have it on the outside, because you can imagine that if we just have the stair towers, when things start really twisting, and the stair towers are just the kind of on the interior and they don't have as much panel action, having the shear wall on the outside is more stiff than having the shear wall in the core. Just because, well, you can see it, there's more surface area to resist, to resist the forces. So we need something in the XZ, we need something in the YZ. So we need something maybe in here, and we need something in the XY. Now, why don't we usually worry about bracing in the XY? Anybody know? Like, in other words, why aren't we worried about bracing in this dimension?
Do you usually have floors anyway?
Exactly. The floors, we have often steel pans and concrete floors there anyway. So the floors themselves act as the shear wall. Of course, not a wall, it's a floor, but they act as a shear wall. And that's why we have what are called shear studs that tie the pan onto the concrete, because that way the concrete can couple properly with the steel frame and resist it that way. So you need something to resist it in each of those three dimensions. It doesn't have to be on the facade, although it can. It's probably more efficient if it's on the facade, and especially in an earthquake. And it doesn't have to be all the way across. It can just be usually, a quarter or a fifth or something like that of the width. And it does have to go all the way from bottom to top. And it does, and you can't, obviously, if you have something like a shear wall, if you made this a shear wall, you can't then you can put some windows in it. There are rules of thumb and rules of calculation. But if you have a giant opening down here, then that's going to be a problem. That's called the soft story problem, where we have maybe a storefront on the bottom floor where it's all glass, and so it's unable to resist on that floor. Well, then it renders this not very effective at all. The whole thing collapses onto that floor, and we don't want that.
So for bracing, we cannot put it in interior, right?
No, you can. You can absolutely put it in the interior.
As well as bracing and moment. Okay, got it. Thank
Yeah.
you. I was confused. I just thought that we had to brace the outside, the envelope of the building.
No, again, it's more effective if it's outside. Because again, all right, here are two buildings right here, right? One of them has a shear wall core and a frame that's an exterior that's not shear wall, and the other one has a shear wall on the outside, let's say, all the way around. And you can see not only does the top one have more surface area to resist, but now we're shaking the earth and we're wiggling it this way and this way. And you can see how this building here is going to collapse first. This shear wall will help it resist the forces to an extent, but if it was a major earthquake that lasted a long time, eventually, if it was a big enough earthquake, the bottom one would be more likely to have structural problems than the top one. It's like a lever too, right? So all this weight of the building is wiggling around this core, in this case, versus this one where the skin, when you start doing the twist and wiggling it, the part on the outside is resisting it, so there's less of a lever effect. If you give me a lever long enough, I can move the world. There's less of that. Other questions?
Can you mix and match systems? Like, for example, in the middle bottom example, you were talking about a storefront on level 1 and then like shear wall on top.
Yeah.
What's that effective if it doesn't go down?
Yes, you can.
Have like shear walls on top and then moment on the bottom, so that you can have storefront, or does it have to kind of be like a continuous system?
You can definitely mix and match. You can definitely mix and match systems. The specific example you gave can be problematic because it's so much more weight on top, And that's another, in earthquakes, that's also another no-no, that you don't want it to be top heavy because the top sways and then eventually collapses. So you can have, you know, a little bit of shear wall here, a little bit of bracing there, and that's no problem. But generally, you don't want it to be too top heavy because that has other problems that are somewhat related to lateral forces and seismic. But there's no reason you could, like for instance, there's no reason you couldn't have shear wall on the bottom and then cross bracing on top. No reason at all that you couldn't do that. Any other questions?
Is weak story and soft story synonyms of each other? I've seen both verbiage. I've seen both during my reading.
I'll Google that, but I'm pretty sure it's the same thing.
Okay, thanks.
All right, one more chance to ask questions.
I have one quick question.
Mhm.
Does this pertain to like all 5 types of construction, or are we just talking about one of them?
That's a good question. Generally, bracing is really only relevant in steel frame construction. If you have, is that true? I'm trying to think of an example where I've seen bracing in a concrete structure. Generally, if you have a concrete structure, you use shear walls just because it's hard to grip the bracing onto the concrete columns, for instance, and because you're already there with formwork and concrete contractors anyway. And so in those cases, I think generally in concrete construction, which is obviously type 1, is generally going to be concrete construction because it's, well, not always, right? I think some type 1, if the steel is properly fireproofed, I think you may be able to use steel in type 1. I'm not totally sure, but basically, when we're talking about, so all structures generally have to resist lateral loads. When we're talking about wood structure, it's usually the OSB on the exterior of the building that does the job. When we're talking about concrete structures, it's generally the concrete itself and all of the connections. If there's enough steel in it, if there's enough rebar in it, it essentially will act like a moment connection where the column meets the floor plate anyway. So, and that's why sometimes, like in older buildings that were concrete, you have those mushroom capitals where the floor plate was like this. The floor plate was like this. And so that was providing essentially a moment connection at the top so that we didn't have to have cross bracing like in old factories. Nowadays we do it, but we often do it more rectilinear because now labor is more expensive now. And those mushroom capitals were pretty difficult laborious to make. But you'll often see that at the top of columns, and that's essentially making it a moment connection. And there's a bunch of steel, I'm not quite sure of the pattern, but there's a bunch of steel that's going to be connecting the column to the floor above and to the floor below. And so that will serve as the kind of connection. So generally in concrete structures, we're talking about a joint at the top of the columns that's going to make the whole thing resistant to lateral loads, or we have concrete walls that themselves are going to act as shear walls. In wood systems, as I mentioned, we have the OSB on the exterior. So generally, if we're talking about bracing, we're talking about a steel structure.